Hey y'all! Well, one of the things we've done a bunch of on this channel is dealing with tube power supplies and dealing with amplifiers that eat rectifier tubes. And there's a very good reason why that happens and why some amps require very specific rectifier tubes, or like you can only use like heavy duty new old stock rectifier tubes, and if you put something like a JJ or some of these other new production tubes that aren't made as rugged as those old ones were, that they blow up and or lightning storm inside and blow fuses. And I've seen a lot of issues like this, had a lot of emails and stuff about it, and so I decided to put together a video to try to explain what's going on with the first capacitor in the power supply versus the rectifier tube. And while it makes sense that you want to put a big enough cap in there to get rid of the ripples so you have nice clean DC into your amp, you have to be careful, and it's a real balancing act to make sure that you're not destroying your rectifier tube in doing so. And there's some really bad power supply designs out there. So I thought this was a good opportunity to try to visually explain what's going on beyond just the inrush current filling the capacitors, because I feel like that when you look online, that's all anybody talks about. And there's more going on than just that. So let's dive into this. Okay, so first let's look at a couple of power supplies that would be used in the same amplifier, but two different types. This is a single choke power supply, and over here we have the power coming in that's alternating current. It goes to this transformer, steps up the voltage. The center tap of the transformer, high voltage winding, is connected to the ground. So we have alternating current coming out of this winding, and one of them does the positive wave, one of them does the negative wave. So positive wave will come through here, goes across this rectifier tube, which is two diodes. So the voltage can only go in one direction. And so you have one positive waveform go through, goes up through this wire here. And I know it's a little confusing because you've got like a 5-volt heater here, which is going across this filament or the cathode, depending on the kind of tube it is. And then off of this pin 8 is what the high voltage to the circuit comes from. So the main thing to understand is you have this alternating current that's alternating between these two plates, and only the positive voltage from each one of these voltage swings off of this center tapped winding will go from this plate to the cathode and then to the circuit itself. Okay, so you have this first capacitor here. You can see this is a 22 UF, much smaller than the second capacitor. This capacitor needs to be fairly small with a tube rectifier, and I'll explain why when we get to one of the next screens. But the first thing you hear people talk about is the inrush current. And that is when you first turn this on, these capacitors are not charged. And so you have what's almost a dead short when the amp first turns on, as it's trying to fill up this capacitor. Now the second capacitor is on the other side of this choke, which has 65 ohms of resistance. And so this slows down the current rushing into this second cap. And that's why this cap can be, in this case, a lot larger. Usually these are more like 220, 330 UF, something like that, but they can be fairly large, and it's not going to destroy the rectifier tube because you've got this resistance here of this choke, and some power supplies don't have a choke, they just have a resistor here. And this is a CLC, which is a capacitor, an inductor, and a capacitor type power supply. There's a CRC, which would be a capacitor, a resistor, and another capacitor. And there are some power supplies that are called choke input, that the choke is the first thing after the rectifier tube, and this capacitor is missing. But most tube circuits are going to have either a CRC or a CLC, which is what this type is. And I'll go ahead and point this out here too. On the 6.3 volt for the heaters on this power supply, the transformer has a center tap on the heaters, and it can be just connected to ground with this one wire that's off the center tap. And there's nothing fancy you need to do. So let's look at another one here. Okay, this one has two chokes. It's got this same 5 Henry choke here. It's got a smaller 2 Henry choke here. And because there's two chokes, you can get the same ripple or millivolts of AC left on the B plus using smaller capacitors because you have two stages of filtration. And this makes it a little easier on the rectifier tube, but you end up with about the same quality of DC, whichever one you use. And again, this first capacitor is a small 22 UF. Now, on this heater, doesn't have a center tap, so what we do is we put a 100 ohm resistor from each leg of the AC to ground, and we've created a virtual center tap by using a couple of 100 ohm resistors. And just wanted to point that out. That's a different way of getting a center tap for a heater by doing this and not just leaving the heater floating, which can cause hum and other issues with a filament supply. So the main point of this video is I want to try to explain what these capacitors are doing. So let's go back to this one. So when you first turn the amp on, one way to visualize charging a capacitor is to think about like a water tower at your city's water supply. And when you first turn on the water pumps, it has to pump the water up the pipe into the tank and fill the tank up. And the whole purpose of those water tanks is to smooth out the water pressure so that if there's a high demand, the water can flow out of the tank into the water pipe to try to keep the pressure or the voltage constant at this point in the circuit. And it's one of the reasons it helps to have a big capacitor like this when you don't have a lot of filtration, so that if there is some ripple in the DC, that this capacitor will be constantly putting voltage into those low spots to smooth out those ripples in the DC, and the voltage will stay constant. So hope that kind of helps you visualize what a capacitor is doing. So here's a little animated GIF showing how a rectifier circuit works. Now this is a full bridge rectifier. There are some tube amps that use a full bridge rectifier. The Wilsonton R8 uses a full bridge rectifier. So, you know, there are some tube amps that use this type as well. But you can see you've got this up and down. You know, the zero would be across this middle here. And then it turns it into this lumpy looking DC. And then what the capacitor does is it smooths it out to look like this. So here's a little drawing here that I'm going to use to try to explain why the size of that capacitor is so important. And if you look at the tube data sheets it shows that you can use different size first capacitors depending on how many milliamps of current you're requiring of the rectifier tube. So when the DC comes out of the rectifier tube, it looks like this orange line here. And like this is 0. This is our voltage this direction, and this is over time. And you know, when it was AC, it would go like this, and then it would go down and back up. Well, the rectifier tube turns it into this, so that all of the voltage is above the 0 line. But this would make crazy noise in the amplifier, and this needs to be as straight a line as possible in an audio amp. So when we're using a 22 UF cap for our first cap, what happens is when the voltage drops off, the cap is like the water tank, and it attempts to flatten out or, you know, fill up this voltage void with positive electricity. So when the amplifier is drawing current along this path here, between this time point and this time point, it's pulling the electricity that it needs from the capacitor, not through the rectifier tube. It's pulling it out of that first capacitor. Then once it gets down to this point right here, the rectifier tube turns back on and starts passing current, and it fills the capacitor back up, and then shuts off again, and then it coasts, letting the capacitor fill in this voltage that's missing because of the way the rectifier tube is making pulsing DC. So the key thing to understand here is from this point and this point in time, there's no current flowing through the rectifier tube, and all of the current that the amplifier is using gets pulled through the rectifier tube during this time window as it's filling up the cap and also supplying power to the amplifier, the output tubes, and all that other stuff. So this time period from A to B across here, all of the current, like let's say the amp is pulling 100 milliamps. So it's pulling 100 milliamps across this whole time period, right? But the current can only flow through this time, and not only does it have to supply the 100 milliamps of the amplifier usage, it's also having to fill that capacitor back up, which could be another 100 milliamps. So you could easily have a couple of 100 milliamps of current going through the tube in each one of these windows. And the reason the tube can handle it, not overheat, is it has this coast period here where it can cool back down before it's got to conduct the 200 milliamps across this charge window. Okay, so let's take a look and see what happens when we triple the size of this first cap. We think, 60 UF cap's not that big. And you're thinking, ooh, yeah, we've cleaned up a lot of this ripple. Look, we don't have near this voltage drop that we used to have. But look what's happened as far as the time window that the rectifier tube has to charge the capacitor back up. There's the 22. There's the 60 UF. We've now compressed the time that same amount of energy that needs to fill up the cap and also supply power to the amplifier in half. So what we've done is during this charge window, we doubled or tripled the amount of current that's spiking through the rectifier tube. And yeah, it gets to cool off for a longer period of time as well. But this amount of electrical energy, and it's easier to think of it instead of current or voltage, but as like a unit of electrical energy. And let's say it needs 10 units of electrical energy. If you're having to supply that same 10 units in half the time, you're doubling the amount of current that's having to go through the tube to put those 10 buckets of electricity back into the circuit. When you put a bigger cap, you cut the time period in half, and so you're doubling the current that's spiking through the rectifier tube during this shorter period of time. And this was kind of a complicated thing for me to understand, and I'm a very visual learner, and seeing this, that you're shortening the period of time that the current can actually flow, because the rectifier tube is not going to let any electricity flow until it gets below a certain point, and then it's going to come through. And so if you've got this bigger cap, it's going to shorten the time window that the rectifier tube has to supply that amount of energy into the amplifier. And I hope that makes sense. I know it's a little confusing, and it took me a little while to get it through my head what exactly is going on and why having a big first capacitor is so bad for a tube rectifying amplifier. But this is what it's doing. And if you put like a 300 UF here or a 330 UF cap, that window gets like this narrow. And yeah, you don't have much ripple, but you also have very little time for the rectifier tube to pass that 100 milliamps of current that the amplifier is drawing. And so that's what kills the rectifier tube. Now, again, if you have this 470 UF cap here, it's almost a dead short. And even though this is a slow start rectifier tube that ramps up slowly, and that's one reason you can get away with having this big cap here as the second cap. If you had like a directly heated rectifier tube that turns on pretty instantly, it probably couldn't deal with a second cap this big. But a 5A or a 4, I found, can handle this when it's on the other side of a choke. So anyway, I hope these two screens kind of help you visualize what's going on and why we need to keep this first cap small when you're running a tube rectifier. And I think it's a good place to wrap up this video. Well, I hope this video helped you understand what's really going on with rectifier tubes and their relationship to the capacitors that are used to filter the pulsing DC into smooth DC that, especially on a single-ended amp like this, needs to have clean DC so you don't hear the noise in the speakers on the output of the amplifier. And I know, I may not be describing all of this in, perfect technical terms, and I'm sure some of you electrical engineers are going to have an issue with the way I describe this, but I'm just trying to describe it in the way that I understand it. And what I'm seeing, bottom line, is the rectifier tube is basically taking gulps of the power out of the wall outlet. And if you shorten that window that the tube can breathe current through it, it's going to have to take bigger gulps to get that same output at the other end of the power supply. And that stresses the tube out when you shorten that window too short, putting too big a first cap. And while it might not kill the rectifier tube immediately, it's why some of these amps, you put a rectifier tube in it and it's good for a couple of months, and then you go turn it on and it does a lightning storm. it's not the inrush current specifically that's killing it. It's that you've stressed out that tube and you've damaged it while it was running to the point that the next power turn on, it just gives up the ghost. So anyway, I hope that made some sense to you. I hope that helped you understand what's going on with tube power supplies, why they need to be designed in a certain way to keep them from eating rectifier tubes. And again, thanks to all you subscribers. If you're enjoying this content, please subscribe. Please like the video. Thanks to all you Patreon folks and also you folks that support me via donations at my website. That really inspires me to create videos like this to help teach you how to build DIY tube gear on a budget. Till the next video, have a nice day.